So this video is going to review the different types of exponential functions, such as growth and decay. So our general exponential function is always written in this form. Now that one form is actually describing two different relationships. Like for example, if I wrote this, y equals 10 times 2 to the x, the idea here is we know from before that we're starting at 10 and we're multiplying by 2 over and over and over again. So like 10 would then turn into 20, and then 40, and then 80, so on and so forth. So our numbers are growing, they're getting bigger. If I wrote a different example, maybe something like y equals 10 times 1/2 to the x, here we would start at 10, and I would multiply by 1/2 over and over again. So 10 would turn into 5, that would turn into 5/2, which is like 2.5, and that would turn into 5/4, which is like 1.25. So we can see here that we're getting smaller, and that word is decay. So we know that an exponential equation can either get bigger, which we're going to call growth, or it can get smaller, which we're going to call decay. Now, if we know specifically that it's growth or decay, we can rewrite this formula in a specific and new way that gives us more information. So if something is a growth, we can rewrite this equation as y equals a times. Now, instead of the number b, we're going to rewrite b as 1 plus r. Now, if it's decaying, we're going to rewrite that formula as y equals a times 1 minus r to the x. So let's make sure we keep track of our letters. So wherever we see an a, whether it be in this form, or this form, we know a is always our starting or initial amount. So I'm going to label that as the start value. Do that same thing over here. Now, originally, we called that b value a constant multiplier. Now, when we rewrite this b value, instead of writing b, we're going to write it as a number of 1 plus something or 1 minus something. So we have a few more vocabulary words to remind us of. This entire number, whatever was inside the parentheses, the entire number is referred to as like the growth factor if we're doing growth. If we're doing decay, then the entire number inside the parentheses is called our decay factor. What we tend to care about a little bit more is the r value. So this r value, if it's growing, we can see that it's plus r. If it's decaying, we can see it's a minus r. That r value is called, like on growth, it's called the growth rate. If it's a decay function, that r value is called the decay rate. So here's a quick example with two different equations. So we can see here that since this one has the number 10, that's where we start. Now, the first thing I'm going to realize is that I have a plus sign here. So this is exponential growth because there's a plus sign. So this number here, r, is 0.50. So our rate of growth, we turn into a percent, is 50%. Down here, since there's a minus sign, I can tell that this is exponential decay. So here I'm starting at 500, but this r value is 0.75. So the rate of decay is 75%. Now, the most fundamental understanding that I think will help you with problems like this is we already know in this format, A is referred to as our start. But what we can start to see is whatever number is in the parentheses, whatever number, this is the percent of your start you keep each time. So let's think about a specific example. What if I wrote this? Y equals 500 times 0.50 to the power of x. So what I can see here is I'm starting at 500. Now, whatever number this is, I'm going to go ahead and do a little side work over here. The number 0.50 as a percent is 50%. So what I can interpret this as is I'm starting at 500 and I'm keeping 50% of it. Well, I could then conclude that I must be decaying because I'm losing. I'm only keeping 50%. If I started with 100% and I'm only keeping 50%, that must mean I decayed by 50%. Let's consider a function like y equals 10 times 1.35 to the power of x. I interpret this as I start at 10. We're going to keep whatever this number is as a percent. So 1.35 as a percent is 135%. We're going to keep 135%. Well, the idea is I'm keeping more than I started, so I'm growing. And if I start with 10, let's start with 100%. And I keep, or maybe you can think of it as I end with 135%, I must have grown by that 35%. So just summarizing in general, what we can think about these percentages. In our original formula, I want you to think of this 1 representing 100% of the starting value. So then the plus sign is going to mean add this much percent. So again, that 1 is represented. We're always starting with 100%. So like if my constant multiplier we saw before was 1.35, I started with 100%. And then I must have added the 35% to get 135%. So the 1 is representing 100% of your starting value. Same thing over here. That 1 represents, 1 as a percentage is 100% of the starting value. And then here we're going to subtract whatever percentage that was. So that's why I see the 1, the plus would tell us we're increasing, the minus would tell us we're decreasing. So here we need to write an exponential growth or decay formula. So we start with $5,000 in sales, and the sales grow. So as soon as we see that word, we know it's exponential growth. So if it's exponential growth, then we're growing by 65%. Exponential growth is in the form y equals, our starting value is $5,000. We start with 1, and then we add the amount that we grow, but as a decimal instead of a percent. So 65% is the number 0.65. So I'm going to add 0.65. If you wanted to, you could also write it like this. Right? If I grow by 65%, that means at the end of it, I'm going to keep 165%. So here we can represent that as keep 165%. Either one of these is an acceptable answer. In the one below, we have a car that starts at the value of $10,000, but it decreases by 35% each year. So if I decrease, we know this is an exponential decay. So we started with $10,000. And then from 100% of that value, we're going to subtract 35% of that value each year. So 35% as a decimal is 0.35. So you could choose to write it like that, or if you wanted to, 1 minus 0.35 is actually the number 0.65. So either of these would be acceptable. So the last set of examples here, we have to determine if it's growth or decay, and then tell us at what rate it's growing or decaying. So the first ones I think are explicit, right? These ones are written explicitly with plus or minus signs, where the ones down here, there's no plus or minus sign. So there's two different types of problems. So when there's a minus sign, I can clearly tell it's explicitly telling me the answer. So I think of this as an explicit problem, meaning I see the negative, so I can tell right away that I'm losing a percent, so this must be decay. And by what percent? Well, if I see the minus sign, this is the percent I'm losing. So I'm decaying by 67%. Same thing over on the one to the right. I consider this what I call an explicit. It tells us the answer without even having to do very much. It's explicitly given to us. It's right in front of our eyes. So because I see the plus sign, I know right away that I'm growing because I'm adding something to my 100% that I started with. So if I'm adding something, I must be growing. And if I'm growing, what percent am I growing by? Well, that's what I added. So 0.10 is growing by 10%. Now the ones below, when there's not a plus or a minus sign, this is where I like to think of it as what percentage that I am going to keep. So like on this one, keep or end with, it doesn't matter. I'm going to start with 10. And then this number here represents keeping 105%. So I started with 100%, and I ended up keeping 105%. Well, I got more percent, so I must have grown. And what percent did I go up by? Well, if I started with 100% and at the end I kept 105, I was growing by 5%. If we look at the last example here, I'm going to start at 50. And I'm going to keep whatever this number is as a percent. So I'm going to keep 75%. So again, if I think about it, I started with 100%, but at the end, I only kept 75% of it. So I lost something, so I decayed. And how much did I lose? Well, I started with 100, and I only kept 75 of it, so I lost 25%.